In this video, we conclude the set of 3 videos looking at matrices and transformations by revising the way in which 3x3 matrices can be used to describe transformations of 3-dimensional space. The specification tells us that we need to concentrate on reflections in the planes x equals 0 or y equals 0 or z equals 0, or rotations about one of the coordinate axes. In terms of key facts, the first thing is there are 4 results which are very similar to the results for using 2x2 matrices to describe transformations of 2-dimensional space. So for the transformation xyz goes to a matrix times by xyz, the image of the origin is always to the origin. The image of the point 1, 0, 0 is the first column within the matrix. The image of 0, 1, 0 is given by the second column of the matrix, and the image of 0, 0, 1 is given by the third column in the matrix. And we also have the fact that if a transformation S is given by the 3x3 matrix A, and the transformation T is given by the 3x3 matrix B, then the transformation S followed by T is given by the matrix BA. The 3 reflection matrices that we will come across is the fact that the matrix -1, 0, 0, 0, 1, 0, 0, 0, 1 gives a reflection in the plane x equals 0, and then a similar result for a reflection in the plane y equals 0, and a similar result for a reflection in the plane z equals 0. Now you have a choice. You might like to remember these 3 results, or alternatively you can answer questions by simply thinking about what happens to the points 1, 0, 0, 0, 1, 0 and 0, 0, 1 under the transformations. We then need to think about rotation about the axes, and the major thing is trying to make sure that one's got the sense of the rotation sorted out. And one way of doing that is that imagine you are looking along the positive direction of the axis of the rotation and that you are looking towards the origin. If you're doing that, you will see the other 2 axes. A positive angle will give an anti-clockwise rotation, and a negative angle will give you a clockwise rotation. For a rotation about the x-axis of angle theta, the matrix is 1, 0, 0, 0 cos theta minus sine theta, 0 sine theta cos theta. For a rotation of angle theta about the y-axis, the matrix is cos theta 0 sine theta, 0, 1, 0, minus sine theta 0 cos theta. And for a rotation about the z-axis of angle theta, the matrix is cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. Now again, you might decide that you are going to remember these 3 different results, or you've got the possibility of working things out by considering what happens to the points 1, 0, 0, 0, 1, 0 and 0, 0, 1. And we shall see both of these 2 possibilities in the examples that we will be considering in this video. So our first example, we have the matrix 1, 0, 0, 0, 0.8, 0.6, 0, minus 0.6, 0.8, and we're told that this matrix represents a rotation. And we're asked to state the axis of the rotation and find the angle of the rotation, giving your answer to the nearest degree. Well, our first observation is simply that looking at the first column of the matrix, we can see that the image of the point 1, 0, 0, which is always given by the first column of the matrix, so we can see that the image of 1, 0, 0 is actually 1, 0, 0. So the point 1, 0, 0 lies on the axis of the rotation, so the axis of the rotation is the x-axis. Now, looking at the second column of the matrix, we can see that the point 0, 1, 0 is mapped to the point 0, 0.8, minus 0.6. We now need to have a think about the convention about directions of rotations. So we must imagine that we are looking along the positive direction of the axis of rotation. In other words, we're looking along the positive direction of the x-axis towards the origin. If we look along the positive direction of the x-axis towards the origin, we will see the y-axis and the z-axis looking like this. Point 0, 1, 0 and its image under this rotation are now added, and we can see that we have a anti-clockwise rotation through a angle which is clearly a reflex angle. To calculate this reflex angle, it's much easier in fact to calculate the acute angle, and for that acute angle we have a movement in the y direction of 0.8 and a movement in the z direction of 0.6, so we can say that tan theta is 0.6 divided by 0.8, so we've got theta is 36.9 degrees. So the rotation that we've got is 36.9 degrees in a clockwise direction, which we can interpret as being a rotation of minus 36.9 degrees, or if we like 323.1 degrees, remembering the convention that a positive rotation is in the anti-clockwise direction. Our second solution for this question makes use of the fact that we might decide to remember the three formats for the rotation matrices. The matrix in the question clearly is similar to the first option of the three, so we can say that it's a rotation about the x-axis, and we can also see that cos theta has got to be equal to 0.8, which certainly tells me that theta is either 36.9 degrees or 323.1 degrees. But we also need that sine theta has got to equal minus 0.6. And sine theta equals minus 0.6 gives me possibilities of 216.9 degrees or 323.1 degrees. So the angle of this rotation must be 323.1 degrees. Moving on to our second example, we've got to obtain 3x3 matrices which represent the transformations A and B, where first of all A is a reflection in the plane z equals 0 and B is a rotation about the x-axis through 60 degrees. So our first solution, we'll think again about the points 1, 0, 0, 0, 1, 0, 0, 0, 1. So, quick sketch showing the plane z equals 0, which is the plane that contains the x-axis and the y-axis. The point 1, 0, 0 is on the plane z equals 0, so when it's reflected in that plane it just stays put. So we know that 1, 0, 0 goes to the point 1, 0, 0. Similarly, the point 0, 1, 0 is on the plane z equals 0, so after the reflection it stays put, it's still at 0, 1, 0. Finally, the point 0, 0, 1 gets mapped to the point 0, 0, 0, minus 1. So putting these three pieces of information together, we can say that the matrix for a reflection in the plane z equals 0 is the matrix reading across 1, 0, 0, 0, 1, 0, 0, 0, minus 1. The first column is the image of 1, 0, 0. The second column is the image of 0, 1, 0. The third column is the image of 0, 0, 1. Similarly, for the rotation matrix, we've got to do a rotation about the x-axis through 60 degrees. So again, it's a good idea to start off by saying, since we're doing a rotation about the x-axis, the point 1, 0, 0 is mapped to the point 1, 0, 0. Now, to think about what's happening to the y and the z axes, we need to remember our basic convention for picturing these things, and we are going to look along the positive direction of the x-axis towards the origin, in which case we shall see the y-axis and the z-axis looking something like that. If we think about the point 0, 1, 0, first of all, rotate it around by 60 degrees, we're going to get as the image point 0, cos 60, sin 60. So the image of 0, 1, 0 is going to be 0, a half, root 3 upon 2. Similarly, we need to consider the image of 0, 0, 1. And the point 0, 0, 1, once it's rotated around by 60 degrees in the positive direction, in the anticlockwise direction, becomes the point 0 minus sine 60 cos 60. So we know that 0, 0, 1 gets mapped to 0 minus root 3 upon 2, a half. And we can now write down the matrix B. The matrix B is going to have the first column is the image of the point 1, 0, 0. The second column is the image of the point 0, 1, 0. And the third column is the image of the point 0, 0, 1. So we've found A, we've found B. We can now move on to the final part of the question. Find the matrix M, which represents the transformation A followed by B. So the matrix M is going to be the matrix for transformation A, which is the first transformation, pre-multiplied by the matrix for B, which is the second transformation. So there's the matrix multiplication that we have to carry out, and performing that calculation we end up with the answer. Now that gives us our first solution for this example. The second solution for this example goes back and uses the standard results. Reflection in the plane z equals 0 is given there. So we can just write down the matrix A as being 1, 0, 0, 0, 1, 0, 0, 0, minus 1. And then we are doing, for the transformation B, we're doing a rotation about the x-axis. So the matrix B is going to be given by 1, 0, 0, 0 cos 60 minus sine 60, 0 sine 60 cos 60, which is 1, 0, 0, 0 a half minus root 3 upon 2, 0, root 3 upon 2, a half. And then the part B follows in exactly the same way as we saw 2 slides ago. So the matrix for M is the matrix for B times by the matrix for A. So there's the matrix for B times by the matrix for A. And there's the final answer, exactly as before.